mission for the Mars mission. Sita Somasundaram was actually the program director for the Space Program Office. Minal Rohit, she's also program manager for methane sensor on Mars. So many of them have actually been on high positions, right? But they were actually studying things at a high level, at the planning level. So let's start off with history. So we do not, unfortunately, it's very sad. I have been searching on the net, but we hardly have any information about Indian scientific women, Indian women who did science. We have very little information about them. And so therefore we are forced to go to other sources. But we should actually have a better, a cover, a better description of women astronomers or women scientists from India. But let's start with Hypatia. Hypatia was in Alexandria, Egypt, and her father was basically a teacher, and she learned from her father, and therefore she was a philosopher, an astronomer, and a mathematician. And she was actually the head of the school in Alexandria. She actually taught philosophy and astronomy. But you can see that at those times itself, there was a big bias people had, obviously, against women doing sciences. And therefore, what you see in this picture over here, that Hypatia had a very tragic end, where actually she was murdered by a mob of Christians. You can see the picture over here, which was there in the previous one. And though she was a prominent thinker of philosophy and astronomy, but unfortunately she went through a very tragic end, and which was definitely not what she was made for. Let us jump a little bit. We'll run a little bit ahead. And if you come to Mary Somerville. So she was actually a Scottish scientist, writer, polymath, and she actually studied mathematics and astronomy. And at that time, the Royal Astronomical Society, we know that we don't have time to talk about that today, but specifically in European colonial times, it was obviously very important for them to capture the seas. And if you wanted navigation in the seas, the most important way to do that was through astronomy. And therefore Great Britain and France had their own observatories, and they were very keen on observations of the skies, because the observations of the skies is what would help them in navigating over the seas. And Britain had the Royal Astronomical Society, which basically promoted astronomy in Great Britain. And Caroline Herschel, we'll come to her in a minute, and Mary Somerville, they were amongst the first female Royal Astronomical Society members. So till then, you basically had all members of Royal Astronomical Society were always men, and you had these women coming in as members. Now, Mary Somerville worked on various areas. For example, the magnetizing power of the refrangible solar rays, on the mechanism of the heavens, and various things. She worked on various aspects of astronomy, mathematics. And then we spoke about Caroline Herschel. Now, luckily, in the case of Mary Somerville, she actually studied and taught. But Caroline Herschel, in her case, what happened is that she was officially not the astronomer. The astronomer was her brother, William Herschel. And William Herschel had a very good telescope, and he was an astronomer. And Caroline, as the sister, she actually assisted her brother in his observations. But she was a very good observer herself. And therefore, she discovered several comets, of which one of them actually got named after her. And that's when her capability was recognized. And the king actually granted her an annual stipend of £50 as William Herschel's assistant. So in principle, she was the first professional astronomer, in the sense she actually got a salary, right? She was the first woman to actually get a salary as royal astronomer. And she also got a gold medal from the Royal Astronomical Society. And along with Mary Somerville, she was amongst the first honorary members, female members of the Royal Astronomical Society, as well as the Royal Irish Academy. So that was Caroline Herschel. Now, later on, we had Maria Mitchell, and Maria Mitchell was also an astronomer, librarian, naturalist, educator. And again, while observing the skies, she discovered a comet which was named after her, which was called Miss Mitchell's Comet. And again, she got a gold prize. See, those were the times when people were very keen at looking up at the skies because they always thought that the sky would come with messages, right? And specifically comets. Comets were attributed because these comets were chance events. Suddenly you have a comet in the sky. The stars were kind of constant. You had a fixed pattern of stars appearing, rising, setting, etc. But comets were like guests in the sky, and therefore comets were given a lot of importance because it was always thought that a comet is an indicator of something that is to happen, right? And so at that time, like how when Caroline Herschel discovered her comet, when Maria Mitchell discovered her comet, she actually got a prize by the king because the kings would actually award people who found comets, because comets, like I said, were considered as important indicators, and they were very important to be observed. Now, Maria Mitchell was amongst the internationally first known woman to work as both a professional astronomer and a professor of astronomy at Vassar College. So she was the first one who actually got that kind of a job. And again, she was the first woman to be elected fellow of the American Academy of Arts and Sciences, as well as the American Association for the Advancement of Science, right? So that's Maria Mitchell. This is not a long time back, right? This is like 200 years back, not a long time back. But we'll move further on, and we can come to somebody who's a really very important person in astronomy, who's so even for their times, what Maria Mitchell were doing and Caroline Herschel were doing was something very important, because like I said, the discovery of comets was attributed to more important events. Margaret Burbidge worked on something very important, which is called stellar nucleosynthesis. Now, what it basically means is that you try to see how do stars synthesize elements. We know that the universe is basically made up of hydrogen and helium and a very small amount of heavy elements. Now, stellar nucleosynthesis is the branch of astronomy which actually studies how do stars synthesize heavier elements. Now, they do that by reactions which are nuclear fusion reactions. So what you can see in this image over here is there is what is called the pp chain, which is the proton-proton chain. There is the CNO cycle, carbon, nitrogen, oxygen cycle, and there's a triple alpha reaction, which is when you have 3 helium nuclei, they merge together to give you a carbon atom, right? So based on the temperature of a star, you have different kind of fusion reactions taking place. So if you see the temperature of the sun, the basic fusion reaction in the sun is the proton-proton chain. While for other stars, supposing the star is much more massive, then the star is generally more hotter, and in hotter stars, the CNO cycle and the triple alpha cycle, they play a much more important role. So what Margaret Burbidge was doing is, in Margaret Burbidge's case, her husband, Geoffrey Burbidge, he was also an astronomer. So most of the work that Margaret Burbidge did was along with her husband, Geoffrey. And Margaret and Geoffrey together worked with William Fowler and Fred Hoyle at the University of Cambridge, and they were studying nucleosynthesis, right? How do stars actually synthesize light nuclei to give you heavy nuclei? And this was very, very important work, very path-breaking work that William Fowler, with whom she was working with, he actually shared the Nobel Prize in 1983 for this work on nucleosynthesis. But unfortunately, when Fowler got his Nobel Prize, neither Margaret Burbidge nor Geoffrey Burbidge, neither of their names were included in the citation of the Nobel Prize. It was just given to William Fowler, though even their publications were done jointly, and everybody was reasonably aware that Margaret had also played a very important role in this thing. But there were some very important things about Margaret Burbidge's life. She continued, she was very hardworking, she continued working in spite of the amount of, resistance which she faced being a woman. And finally, if you actually see, Margaret Burbidge, she even became director of the Royal Greenwich Observatory. And that was a very prestigious position, right? And in principle, generally, the director of the Royal Greenwich Observatory was also the Astronomer Royal. And but the Astronomer Royal could not be a woman as per the Royal Astronomical Society. And therefore, when Margaret was made the director of the Greenwich Observatory, Martin Ryle was actually kept as the Astronomer Royal. So they still held on to their their plan or whatever, their plan that the royal astronomer has to be a male, and they stuck on to that. But in spite of that, Margaret continued with her work, and she did very good work. At the same time, she also campaigned in opposition to the discrimination against women, because Margaret Burbage, we do not have the time today, but at various stages of her life, she constantly faced problems with her being a woman. For example, when she was observing at Mount Wilson, basically her husband was observing, she was observing, and when they realized that she was observing, they actually said, oh, a woman cannot observe. We do not even have restrooms for women, and we do not have hostel for women. So then that's when, Margaret and Geoffrey Burbage, they actually rented a place so that they could come to the observatory. But so in a way, Margaret Burbage always tried to find a way out. So if there was the rules which were, against her, this thing, she would somehow find a way to work around the rules so that she could continue her work. But a very important thing about Margaret Burbage's life is that, for example, in 1972, she was being awarded the Annie Kennan Award. We'll talk about Annie Kennan in a short while, of the American Astronomical Society, and she refused it. And she refused it for the simple reason that this is an award which is awarded exclusively for women. Now, Margaret Burbage was of the opinion that there is no need to reserve awards for women. Women can compete with men en par, and you do not need to reserve any positions for women. Women can anyway win the prizes they want without that kind of a reservation. And therefore, in 1976, when she became the first female president of the American Astronomical Society, and in 1984, the American Astronomical Society actually awarded her the Henry Norris Russell Lecturership, which is an award which is not only for women, it's open for both gender, and she accepted that award. So that's also something very important which we need to remember from her life, is that her point was that there is no need to reserve awards for women. Let women compete en par and they can still win, right? Margaret Burbage also contributed very importantly in the working of the Hubble Space Telescope. She helped develop the faint object spectrograph, which is a very important instrument on the Hubble Space Telescope, and also discovered that Messier 82 contains a supermassive black hole at the center. So what Margaret did was actually very important, very path-breaking kind of work, which we have from her with HS. Now let's move on to somebody also who's also very, very important. That's Vera Rubin. So you have Vera Rubin. She was also an observational astronomer, and she was actually observing what are called galaxy rotation rates. Now, what are galaxy rotation rates? I'm sorry, I think I don't have a picture over here of that. No, I don't. So, galaxy rotation rates are a plot of velocity versus radius. So, what you actually do is you observe stars or various objects in a galaxy. You do their spectroscopy and get their velocities. And then the galaxy rotation curves were plots of velocity versus radius or distance from the center. And Vera Rubin was observing this. I'm sorry, I do not have a plot of this. I should have actually had one. And what was observed is that typically what should be there is that if you had Keplerian kind of orbits, then as the distance from the center of the galaxy increases, the velocity of the galaxy should fall. Okay? But what Vera Rubin observed is that the velocity of stars in the outer parts of the galaxy instead is very, very high. They actually move at very large velocities. Now, to explain that, she did not know how to explain it, because if you have a matter in the center of a galaxy, which is the center of mass, then obviously as you move from the distance, right, from the center, you will obviously have as r increases, the velocity should fall, right? But the problem is, she saw it was not falling, and the only way to explain this was very weird, with something called dark matter. Now, dark matter is still a very important problem being studied in astronomy, because dark matter is matter which actually shows its behavior gravitationally. So when you look at stars which are in a region where there is dark matter, you can actually see the gravitational influence of the dark matter on the motion of those stars. But if you actually look in that area, you actually see no emission. There's no emission neither in optical, in X-ray, in no part of the electromagnetic spectrum do you get any emission from these objects. These objects do not emit, but they show their presence gravitationally, and hence they are called dark matter. And that's what Vera Rubin discovered. So, like I said, dark matter is still a very hot issue in astronomy. We still do not know the true nature of dark matter and what is exactly dark matter made up of. We still do not know. It's just that we know that a very large portion of our universe is made up of dark matter, right? 99% of our universe is made up of dark matter, but we do not know what it is. But Vera Rubin was the one who actually discovered it. And like I said, that the lesson we can learn from Vera Rubin's work is that the plots that she got, right, for gravitational rotation curves, they were very counterintuitive, right? They were very different from what we would expect in the case of, in normal rotation. So what she got was something very weird. And since there was no way to explain it, she proposed dark matter, which was also a very exotic thought, right, that there is something called dark matter. But Vera Rubin had the confidence in her data, in her measurements, in the plots that she got, that she actually proposed dark matter. And even now, dark matter does show its, through various observations, we have more and more evidence about the existence of dark matter. Though we still don't know well what is the nature of dark matter. But Vera Rubin gave us this about dark matter. Now we'll have to rewind a little bit because I want to talk to you about a group of women called Harvard computers. Now at Harvard, that is in Boston in the US, you actually have an observatory which is the Smithsonian Observatory or the Harvard Observatory. Now the Harvard Observatory in those times, what it basically did is they had photographic plates, and using photographic plates they would observe large amount of parts of the sky. Now the problem is that they generated a lot of data. There were loads of photographic plates from the data they got night by night. But the problem is that somebody needed to observe those plates and inspect them to make sense out of them, right? And therefore, you can see in this image, the person over here, he's Pickering, Edward Pickering. Now, Edward Pickering was the director of the observatory, okay? Now, the problem is he had loads of these photographic plates, and somebody had to do this very monotonous, boring, tedious job of actually inspecting photographic plates, of cataloging the presence of stars, of measuring their brightness. The brightness was measured by measuring the size of the dot that the star caused. So the larger the dot, the brighter the star, and actually labeling all the plates. And this was obviously considered a very tedious, monotonous, mundane kind of a job. And therefore, Pickering, what he did is he hired a set of women to do this kind of a job, because this was considered to be very mundane kind of work, right? And he actually hired this bunch of women, most of them who are now very famous. There's Annie Jump Cannon, Henrietta Leavitt, Cecilia Payne, Antonia Maury, and a whole bunch of other women who actually worked with Pickering on the data they got from Harvard Observatory. Now, in a humorous way, they were also called Pickering's harem, because Pickering was very confident that women can do their work very well. It is often observed by people that women are much more keen observers of detail compared to men. Now, I know there could be men in the audience who could argue about that, so I won't push that too far. But it is often considered that women have a much more keener eye to detail. I'm just saying this without any proof. You can refute it whenever you want. So that was Harvard Computers. And now let us see what was the very important work that the Harvard Computers did, which when initially it was considered to be a mundane, tedious, boring kind of a job, but it gave them very brilliant results. About is Henrietta V. Now, Henrietta plates, you needed to mark every star, okay? Give it some number, a catalog number, mark the star, and then measure the brightness by measuring the size of the dot it created on the photographic plate. And the brighter the star, the larger would its dot be. Now, what Henrietta Leavitt did is, while she was observing these stars, she observed a bunch of stars which are called Cepheids. Now, Cepheids are variable stars. And what was observed, that these are variable in the sense they have varying brightness. So what happened is that she observed that the variation, the time period of variation of the brightness was directly proportional to the brightness of the star. That means the brighter the star is, the longer would it be its period of variation, right? Another very important thing she realized is that Cepheids, these were called Cepheids, and they realized that Cepheids are what are called standard candles. So in astronomy, we have a concept called standard candles. By standard candles, we mean an object which has a certain brightness, okay, which has a fixed brightness. It's like a 100-watt bulb. You know that the 100-watt bulb has a fixed brightness of 100 watts. But the biggest problem in astronomy is distance. How do you measure the distance to an object, right? So if you want to know the intrinsic or the real brightness of an object, you need to know its distance. Because otherwise, you could have a bright star which is very far from you and hence you think it's faint. Or you could have a faint star which is very close to you and hence it looks bright. Now with Cepheid variables, the good part was they are what are called standard candles. By standard candles, you mean to say stars which have a known brightness. And therefore, Henrietta Leavitt put 2 and 2 together. One thing is that Cepheid variables are standard candles. That means you know the brightness of the star. The second thing is she found the law which said that the brightness is directly proportional to the period, right? Now, while you observe these stars, you can easily observe the period. In the sense, you can measure the brightness today, tomorrow, in multiples of days, and you can actually find out what is the period. That means the time taken for the star to come back to the same brightness, right? And so that would be the period of the star. And once you know the period of the star, you look at this plot. I'm sorry, on the y and the x-axis you actually have, here you have period, okay? So if I measure the period, I can say what is the luminosity of the brightness of the star, right? So I know this is what is called the real brightness, right? The real brightness of the star I know by measuring its period. On the other hand, the star, as its distance varies from us, you can see that this very candle is of different brightness at different distances, right? And therefore, if you measure the brightness of the star, which you can through the photographic plate, and number 2, you measure the period of the star, the period of brightness, you can find out the real brightness. With this, you can find out what is called the apparent brightness of the star. And using the real brightness and the apparent brightness of the star, you can find out the distance to the star, right? So essentially what Henrietta Leavitt did is, using Cepheid variables as standard candles, she found a method to find out the distances to Cepheids, right? Now Cepheids are very, very bright stars. These are giant stars, and therefore they can be very easily observed even in other galaxies. The Cepheids we observe are not only from the Milky Way, but they are also from other galaxies, right? So let's keep this in our mind and see how did Henrietta Leavitt's work, play a role. So we know that Henrietta Leavitt found Cepheid variables, uses that to find out distances to stars. And Cepheids are very bright, you can see them in other galaxies. Now, how did this get applied? Now, you know that galaxies are large collections of stars and dust and gas. There's a large mass of them. They have a typical size of about 300 kiloparsecs, where a parsec is 3.26 light years. And in astronomy, we have a unit which is called a light year, which is the distance traveled by light in 1 year, right? So what is the distance traveled by light in 1 year? We know that the distance traveled by light in a second is 3 into 10 power 8 meters per second. And a year has 3 into 10 power 7 meters per seconds. Therefore, you multiply 3 into 10 power 8 multiplied by 3 into 10 power 7. So you get 9 into 10 power 15. So a light year is 9 into 10 power 15 meters, right? And 3.26 light years will give you a parsec, and a size of a galaxy is 1 kiloparsecs, right? It has a mass of about a billion, that means 10 power 9 or 10 power 12 masses. These are galaxies. Now, by then people had started using telescopes and they were identifying galaxies, right? They could look at galaxies with their telescopes and actually identify different galaxies, right? Now, Hubble, most of you all must have heard about Edwin Hubble. Edwin Hubble started observing these galaxies, okay? And what he started doing was he was doing spectroscopy of these galaxies. By doing spectroscopy of these galaxies, you can measure velocities, right? Many of you all may be aware of what is called the Doppler effect. What is the Doppler effect? That if you have a source of light which is moving, then the light it emits, there is a wavelength shift, okay? And that is called the Doppler effect. Now, we are already familiar with the Doppler effect, for example, in the case of sound. In the case of sound, what happens is if you have a train or a vehicle which is going away from you, it sounds different from if it's coming towards you, right? The pitch or the frequency changes. Pitch frequency is the same thing as color or light. So in the terms of light, if a source is going away from you, we say it's red shifted, it becomes longer wavelength. If it's moving towards you, we call it blue shifted, it's coming, towards shorter wavelengths. So Hubble, what he did is he was observing various galaxies using the Mount Wilson telescope, and he used the spectrum to actually measure velocities, okay, of objects in these galaxies. Now the distance to the galaxies he found using Cepheids, okay. So using Henrietta Leavitt's work, he knew the distances to those galaxies. Otherwise there was no way he could find out the distance to the galaxy. He found out the distance to the galaxy using Henrietta Leavitt's work, which is using observations of Cepheids in those galaxies. And then what he did is he made a plot. Here you see the plot on the y-axis has the velocity which he got from spectroscopy, and the x-axis has distance which he got from Henrietta Leavitt's work, that is from observations of Cepheids. And then when he made a plot of velocity versus distance, he got a straight line graph, okay. Now actually if you look at his data which he had in those times in 1929, this had a very large scatter. But if you look at modern data, you'll actually see that the scatter is much lesser with modern values. But anyway, Hubble actually discovered that the velocity and distance, you have this kind of a thing, which was then given as Hubble's law, which is V is equal to, it's proportional to D, which is equal to h naught into D, where h naught was called Hubble's constant, right? So therefore what he discovered that the velocity of a galaxy is directly proportional to the distance of the galaxy. So if this is Milky Way and you have these galaxies at a certain distance from them, they have a certain velocity. But if you have this galaxy which is further away, it has a larger velocity than this galaxy, and this galaxy which is even further away has an even larger velocity. So as you're going away from Milky Way, as the distance increases, the velocity also increases. And this is what is called Hubble's law. And Hubble's law is taken as the direct indicator of what we call the expanding universe. That means our discovery that the universe is actually expanding. If you reverse this, this actually gives you the Big Bang. That means if now the galaxy is expanding, that means if I play back in time, then these galaxies were together at some point of time, and that point of time when they were together is what we call the Big Bang, right? And since the Big Bang, you have the universe expanding. But you can see that Hubble could have never done this thing, because in the formula he has, V is equal to h naught into D, agreed, he did the important work of finding out V, which is the velocity using spectroscopy, but Henrietta Leavitt did the very important job of finding out D, which is the distance, right? And therefore Henrietta Leavitt's work plays an equally important work in our discovery of the expanding universe as Hubble's law, right? It is the very base, it is the basis for Hubble's law. So another plot here I have of Hubble's law, where you have velocity versus distance, and you have this. So that gives us our theory of the expanding universe. Now let's move to another lady who was also part of Harvard Computers. She was actually looking at this. These are photographic plates which are at Harvard, and they're still there in the museum. There's a museum over there which has the plates, and which I've seen. And you can see that Annie Jam Cannon was actually inspecting the spectra of stars. Okay, so from the observatory they observed the spectra of stars, and what she did was something very important, is she actually classified it. I will actually show you. This is what spectra of stars look like. Okay, if you look at this right hand picture, this is how the spectra of stars look out. So what you have over here, this is what is called a continuum spectrum. That means a spectrum which covers all wavelengths from violet to red. And then in this spectrum you have certain dark lines which are called absorption lines, Sometimes you can have some bright lines which are called emission lines, and basically this is what you're observing. This is the kind of thing that Annie Jump would have observed in these photographic plates. What she did is that observing these, she actually classified them. That means she classifies stars into certain categories based on their spectrum. And those categories were O, P, A, F, G, K, M. These various categories she classified these stars in, right? And how did she do it? Based on the strength of the Balmer absorption lines. So if you actually look over here, you have the Balmer absorption line coming, and the hydrogen lines here. So based on these, she actually classified these spectra, and based on that, it was realized that this is related to stellar temperatures. And so to put them in a temperature order, students of astronomy already know this mem which is called O Be a Fine Girl, Kiss Me. So O type stars are the hottest, M type stars are colder. So O, B, A, F, G, K, M. So O is hottest and M is coldest. So she actually classified. So if you actually look over here, this is an image of what spectra look like. If I actually get this in terms of brightness, you can plot it in a spectrum which is normalized flux versus wavelength, and you will get a spectrum of this kind, right? So you have a black body spectrum, and couple that with that, you have these are absorption lines. Here you have some emission lines, but you have some absorption lines. So she actually could classify these spectra. This is very, very important because this was directly related to the temperature of a star. So that means that if you observed a star, if you got its spectrum, that's it. Once you had the spectrum of the star, you could immediately get the temperature of a star. And that is very important information about the star, which you can get using the spectrum. So that was done by Annie Jump Cannon, right? Another very important person from Harvard was Cecilia Payne. And Cecilia Payne was actually working on her PhD in Harvard, where she actually discovered in her doctoral thesis that stars are basically made up of hydrogen and helium. Now at that time, that was a very bizarre result to give, and therefore her conclusion was initially rejected. Okay, because at that time they assumed that the elemental abundances of the earth and the sun is about the same, and therefore it was actually this thing told to her that her her result is wrong. What she derived was wrong, since it was against scientific wisdom. I would also like to bring to your notice how a lot of these women, what they gave out was something which was actually against the scientific wisdom of their types, whether it was Vera Rubin talking about dark matter, or Cecilia Payne talking about stars being made up of hydrogen and helium. Initially it was rejected, but later on with observations they realized that she was very, very right in what she'd said. So you actually have women who are brave, who are good not only for doing good astronomy, but at the same time brave enough to actually declare results which are totally counterintuitive, which are totally against what people believe in, and willing to actually give that as their, as their opinion or as their work. We'll now move to another very brilliant woman, who is Joycelyn Bell Burnham. And Joycelyn Bell, you can see a picture of her here while she was doing her PhD in Cambridge. So she was doing her PhD in Cambridge, and she was working with Anthony Hewish, who was her PhD supervisor. And what they tried to do is that they tried to build a radio telescope to study interplanetary scintillation. Basically, the purpose was to study quasars. And she built this whole wire mesh, huge radio telescope. But what happened is, with her observations with that telescope, she could actually get signals which had certain pulses. It had a pulse, in the sense repetition at a short time interval. And at that time, that was called the little green men, LGM1. The source was called LGM1 because it was assumed that this has to be some kind of an alien signal. Because how would you actually have a natural process giving you a signal which has such a good periodicity, right? Her signals had a very good periodicity. So the question was, how can you actually get something like that? And then later on, she continued her work, with which she discovered that this was not an alien signal, this was a natural signal coming from objects which are called pulsars. Pulsars are objects which show pulsating signals, that means signals which vary in time. And basically because pulsars actually have a very strong magnetic field. And therefore while the star rotates, you do not get the emission from the star. You only get it when the pole faces you. So it's like a torch rotating, lighthouse model. And therefore what Jocelyn Bell did was really path-breaking. She detected the signal and then also inferred that this was from a natural process, which are pulsars. And this was considered a very important result for which the Nobel Prize was given in 1974. But again, like it happened in Margaret Burbage's case, the Nobel Prize was given only to Anthony Hewish. It wasn't given to Jocelyn Bell. And the reason they gave was they said that Jocelyn Bell was only the student, Anthony Hewish was the supervisor, and he's the one who actually came up with the problem, and Jocelyn Bell does not deserve it because she's just a student. But in principle, if you actually look at it, Anthony Hewish had never ever dreamt that he's going to be observing pulsars, right? He thought he was basically making a study for quasars, and that's what Jocelyn Bell was supposed to be doing. So what actually Jocelyn Bell discovered was a accidental discovery, right? It was an accidental discovery, and because it was done by her, ideally speaking, obviously the Nobel should have gone to her, because it was not the the whole experiment was not planned by Hewish to actually find pulsars. It was planned for something else, and by chance, accidentally, she found this out. But anyway, the Nobel Prize committee did not give it to her, and but Jocelyn Bell obviously continued her work, and she's still visiting professor at Oxford, fellow of Mansfield College, and finally, 50 years after that, she actually won the Breakthrough Prize, which is $3 million, and which is 3 times more than the amount given by the Nobel Committee. But Jocelyn Bell has been since then working for women in astronomy, and therefore she donated her whole prize for PhD fellowships to underrepresented physics students and to actually elevate the diversity issues. So Jocelyn Bell is a fighter for women in astronomy, and all her prize money she dedicated to that. The last woman I'm going to be talking about is Andrea Ghez. Andrea Ghez, who actually, she's a professor of astronomy and astrophysics at the UCLA, the University of California, LA campus. And she actually got the Nobel Prize just 2 years back, where she shared it for finding a supermassive black hole stuffed with 3 million suns at the center of the galaxy. And this is by mistake. And so Andrea Ghez, she actually did very meticulous near-infrared observations of the center of the galaxy to actually derive the motions of stars and get the velocity, get the mass of the central black hole. So Andrea Ghez is also a very well-known astronomer. Now let's look back home, because if you realize all the ladies I mentioned to you are all who not from India. So I'm going to focus a little bit about our own scene. We need to be aware about India. We need role models also from India, and we definitely do have them. So I'll talk to you about them. So the first model I'm talking about is Anupama, GC Anupama. I'm sorry, but the text did not come. But India, we have a professional body called the Astronomical Society of India, and GC Anupama is the first female president of the Astronomical Society of India, and so that's her. Annapurni Subramaniam, she's the first female director of the Indian Institute of Astrophysics, which is in Bangalore, and works in various areas, and so in that way, she's another woman astronomer. Chanda Jog is also one of my favorite women astronomers in India. She works at she just retired recently. She's working at the Institute of Science in Bangalore, working in galactic dynamics. And I'm not going to talk about more Indian women astronomers, but there are a whole lot of them working around all over the country. And it's a good idea for you to actually check them out. There are many. And then I'll focus a little bit about ISRO scientists. Most of you all are familiar with the pictures of ISRO and how all our space missions have a good amount of women in there. and you can see that I'm going to talk about some of them. For example, there's Lalitambika, who's actually the woman, if you all must be aware of the Gaganyaan mission, which is the mission which we have of sending man in space, right, which is something which is planned, which would happen very soon, hopefully. And she's actually, 1 minute, Lalitambika is actually leading the Gaganyaan mission, which is, like I said, the mission to send out a man in space, a woman in space, and she's actually dealing with that. Hopefully we'll soon hear good news about the Gaganyaan mission. The other one is Muttaya Vanita and Ritu Kharidar. Many of you all would have seen their pictures. They are actually the women behind Chandrayaan 2. Many of you all must have heard about Chandrayaan 2. You all must have seen the live footage which we had of Chandrayaan 2. And both of these are scientists which are heading. Again, these are scientists which are heading as project director as well as mission director, and for this. And they also, Karidal is also the deputy operation director of the Mangalyaan mission also, right? Then you have TK Anuradha, who is the senior most woman scientist at ISRO, and she's been working with ISRO for more than 35 years. First woman to become a satellite project director at ISRO, and she's worked on various Indian space programs including GSAT 12, GSAT 10, and she is the GeoSat program director at the ISRO Satellite Center. Then Nandini Harinath is a person I'm sure many people have seen her picture earlier. She's a part of the Mangalyaan and various other missions. She works at the ISRO Bangalore Center. So she's project manager and deputy operations director of Mangalyaan, and she's been working with ISRO for more than 14 years. So that's Nandini. And then there's Sita Somasundaram, who's actually a mix in the sense she works in ISRO, but she does work in astronomical problems. So she works in X-ray astronomy. So she's ISRO as well as X-ray astronomer. And she's the program director of the space science program. She has been working with calibration of Mangalyaan, as well as she's been working with Astrosat. She's in Bangalore. And hence I hope I could, with the few examples I showed you of the Indian scene, there are many more women astronomers in India whom I have not covered. I just covered a few just to sample them, just to convince you that it is not that we do not have astronomers in India. We do have astronomers and space scientists in India. And what I was trying to highlight is the ones which are on, higher positions, at leading positions. So we do have a good number of astronomers, space scientists at leading positions in India who are playing very important roles. So I hope in this last 10 minutes, I will just talk to you a little bit about the issues of women in astronomy. So what you saw, which I tried to highlight in this case, is that the capabilities of women are obviously beyond doubt. It's clear that women can do physics and astronomy as well as men can do it. But if you look at this figure over here, this is a figure for physics and astronomy, which are very similar. This is called the scissors diagram. If you actually see over here, you can see 45 and 60. This is telling you the percentage of men and women at different stages. So if you actually see at high school level, you may have 45% of, or 55% of males, 55 male, and you have about women about same, close to 50%. You have a split at high school. But as you go to bachelor's degrees, you see the number of men becomes much larger. You may have about 70% men, 30% women in physics, studying physics. At PhD degrees, again, 80-90% are men, 10% are women. At assistant professors, similar, something like that. And then when you come to full professors, you can see that the number of women are very, very small, less than 5%. This is for physics in the USA. This is astronomy again in the USA, which you can see a very similar diagram, that initially at high school, bachelors, you could have comparable numbers, but as you go to higher levels, you can see there's a clear fall in the number of women. So you can see that you'll have men which are like 85-90%, and full professor women are less than 5%. There is the International Astronomical Union, which is the largest professional body of astronomers in the world, and in that you can see that the percentage of women in the Indian, this thing is barely 7%. This is way back in 2003, right? Less than 10%. So let us see, why do we have such a problem? Why is there such a lack of women in astronomy, right? So one important problem is the stereotypes. Since the time children are young, it is always taught to girls that they, shy away from science. They are kept into other subjects, while boys are encouraged to do science. If girls are encouraged to do science, they are made to do biology or chemistry, but definitely not physics or maths, because that's considered too difficult for women. And therefore, what is important is some kind of a 3-step process. The first step which we need to do is actually educating young girls. We need to educate young girls so that they find an interest in STEM, in doing sciences, right? In science, technology, engineering, mathematics, medicine. And they actually educate them to actually encourage them to do that. The other important step which needs to be done is recruitment. When it comes to jobs, if you remember, if you see the previous thing, you can clearly see that when you come to jobs, you can again have a larger number of men, then you'll have women. And therefore, what happens is, in recruitment, we should ensure that women get a good number of positions when jobs are advertised. And it's not that all the positions are given to men and women are, not given those positions. And then after they're giving their positions, there have to be steps done to retain them. Because then a lot of these women may then start families, they may have children, they may have other responsibilities, but the job should give them flexibility. Now in the pandemic, we actually know that how easy is it for people to actually work from home. For the first time, people realized that people could actually get out comparable outputs even working from home. So if women are, for example, given more flexible working hours, so that they can address their problems at home in the sense of children or elders or whatever responsibilities they have, they can be retained at their workspace if there is flexible working timings which can encourage them to say. So what is important is sensitization, gender sensitization, so that people are sensitive to it, that if you have a woman who needs to leave early because of her children or for other reasons, she should be allowed some amount of flexibility. And like I said, specifically in the pandemic, we have seen that working from home is as good as working from office, right? This is another plot which is again of the same thing, that the demographics, this is the earlier one I showed you was for 2003, right? This one is 2013. Again, you can see that when you are at graduate student level, you may have say 75%, you may have 35-65 break of girls and boys. These are boys and these are girls. But as we go up the ladder, right, to administrator level or full professor level, you can clearly see here that the number of women are like barely 15%, or here 20%, and the rest all positions, everything is just held by men. So women are not there at these higher positions, right? So this is what is called the leaky pipe problem. You started off with a large number of women at high school, at grad level, and then as you move ahead, the number of women falls, and you have, it's at the end of the pipe has leaked, you have very few women. So if you look over here, this is for the US. This is a plot of the US population, right? So the US population shows you that 32% is white female, 31 is white male, and these are all the other the other distribution of people which you have in the US population. But if you look at science and engineering, in principle, this plot should have been a reflection of this. If equal number of people are interested in sciences, you should have a similar plot. But what you see now is something totally different. You can see that 51% of the positions are all held by white male, right, which is only 31% of the population, but these positions are 51%. And then white female, who are 32%, they are only 18%, right? And then if you look at all these other groups, Asian males, females, Hispanic males, females, black male, female, you can see that they fall even more, right? So the amount of representation you have from these other groups, right, is even smaller. So ideally speaking, this image, this plot, which should have been a reflection of this one, is so very different. What I'm basically trying to convince you that is that the problem does exist, and It is a problem for which we need to find a solution. How do you ensure that you have more women in sciences or in astronomy and you do not have the leaky pipe problem? Another very important problem which we have in astronomy is what is called the two-body problem. Very often you have couples who meet while studying, they get married, and then when they look for jobs, since they have similar qualifications, they apply to jobs to similar places. But when they apply to these similar places for jobs, the employer prefers to employ the male than the female. One of the reasons could be that often the male is older than the female, so he may be more qualified than the female. And then often in many jobs, the preference is always given to men because they always feel that a man will be able to do the job better than a woman because the woman is going to distribute her attention between home and work. She will not be able to give her 100%, while a man will do that, and therefore often the man gets employed. And therefore in the two-body problem, what often happens is the man gets a job, but the female, the woman, does not get a job. Either she compromises by taking a job which is not suitable to her, or she just doesn't work. And in either way, it is the loss of a scientific brain, right? So what do we do? How do we actually ensure that our girls, that all of us, the women, actually get to do what they want to do, right? So here is an image of the General Assembly of the International Astronomical Union, right? Now in this picture, I'll show you now, these are the only women in this picture, right? 1, 2, 3, 4, 5, 6. That's it. There are no more women in this picture. The whole General Assembly is just made up of males. This is 1928. And that there are males over here too, right? In 1932, when the General Assembly was held in Cambridge, you can see that there are a few women over here, but again, not too many, right? You do not see a large number of them. The International Astronomical Union has been trying its best to ensure that women are well represented, so that the executive committee, this is for the International Astronomical Union, has a larger amount of women, right? They've been trying to do that. And therefore the second female vice president was from China. The first one was from the US. And then if you actually take the statistics of the IAU members, International Astronomical Union members, you can see that there's been a gradual increase, but it's gradual. So in 1939, 10% of them were female, but in 2021, 21.2%. So that's just an increase of 10%, gradual increase. So it's positive, it's good, but it's gradual. But what is noticed is that in the recent years, if you were to actually check the distribution of this 21.2% of women, you will see that the bulk of them are younger women. That means 35 to 40% of them are younger generation, not older women. So hopefully we are moving ahead in the right way. If you actually see gender distribution in the year 2015, right, you can see even India has less than 10% representation. You have this parts over here. And even if you see the US also has between 10 to 20%, right? Some parts of Europe have more, 20 to 30, and some parts of South America, and here you have more. But otherwise you can see that there are a big chunk of them which are, so the 35-40% category is Bulgaria, Thailand, Argentina. These are the countries in 2015. In 2018, you can see there's an improvement. For example, now India then came into the 11 to 20% category, which is an improvement. Argentina has gone more than 40%. And the US, which was earlier, which I showed you, was in, same 10 to 20%. You have them still same 10 to 20%, which is there for these countries. You have Russia over here with 21 to 30%, right? So that's the distribution across this thing. So various things are being done by the International Astronomical Union to promote women. For example, having more women in high IAU positions in the executive committee. They try to ensure that, which we should also do, that at symposia you have a good amount of female speakers. They organize what is called the Women in Astronomy lunches. Mentoring work is done. There are schools, gender gaps, various things which are done to encourage women to be astronomers. There have been 4 IAU presidents who are women. The present IAU president, Deborah Allen Green, is also a woman. The previous one was also one. 4 also we had. So we had a good amount of women female presidents of the IIU, and various IIU officers also being women. Even the last one which we had from 2018 to 2021, you can see 3 women, 1 man. That's this thing. And the present committee which is there, which is from 2021 to 2024, you can see we have a perfect distribution, 50-50. There are 2 women and 2 men who are the officers on this thing. So you have the president and the others. So in that way, what we are doing is, this is the ideal situation where you have a 50-50% distribution between men and women in the offices of the IIU, right? This general secretary, these are just examples of people who are this thing. The division presidents also, you can see a large number of women. They also keep a check on gender equality in scientific meetings. So the blue plot is invited talks, orange is contributed, and they actually check what is the percentage in female ones, right? So in invited and this thing. So it's still not 50%, but we are still going there. In the General Assembly, they organize what are called Women in Astronomy lunches, which is open to men as well as women. All can attend, and the purpose of this is basically to discuss women in astronomy, right? And they've also, the IIU also organizes international schools for women astronomers, for young astronomers, which also has women in them. PhD prize. Now the good thing is, see, these are the kinds which, like Burbage spoke about, Margaret Burbage, which these are open for all, for men and women. Only that you ensure that in these things you have an equal participation of men and women, right? So even PhD prizes which are given every year, you can see in this, there's no reservation for women, but obviously there are women who do get the prizes, right? It is lesser, like you have 2 over here out of 9, but they're there, there's no reservation. Gruber Fellowship is also given irrespective of gender, but you can clearly see some female faces which actually show you where they are actually getting it without any reservations. That's the way it should go. There is also the IIU 100, which does the Women and Girls in Astronomy events, where there are various astronomy events all over the country, which basically are to encourage women in astronomy, and various events over here. And it is also extended to making astronomy more inclusive, not just women, but also looking at gender, all gender, as well as here you can see this is what is called tactile astronomy, where with 3D printers they print out surfaces, for example, of planets, and you have blind children who actually feel it. So efforts are being made a lot to make astronomy inclusive, in the sense available to everyone who wants to do it, including the physically disabled people also. So what is hoped, even the 2018 General Assembly of the IIU, which had attended in Vienna, for all the plenary talks, they did have these kind of sign language representation, so that if in the audience you had somebody who was hearing impaired, they could hear it and they could actually this thing. So this is being also done a lot in IIU events, especially for plenary talks, to give it with sign language also available to all. And there are specific studies being done on gender gaps and follow-ups for that. It is hoped that in the next 100 years, the International Astronomical Union ensures that astronomy is more inclusive, more diverse, so that everybody interested, everybody who loves astronomy can actually do astronomy. And like I said, there are various things being done. I would also like to give a last word about the International Astronomical Union has a working group for women in astronomy, of which I am the co-chair. Mamta Pomier is the chair, who's here. That's Mamta and that's me. And we have a working group. You can see some of the members over here. And what we are doing is we are trying to do special efforts to help women in astronomy, to encourage them, to help them. And there are various things which we are doing. So we are basically working on a 4-point program. One is to increase the awareness and sustainability of the working situation of women. I am very much focused on training and skill building. That means in teaching women different softwares, teaching them coding, teaching them various things that can help them do science, because if they actually have the skills and the training, they can go forward and do their work. We are also working on doing fundraising, that is to raise funds and provide financial support to women researchers in crucial stages of their careers, because many of them may not have the funding to do their research, to travel for conferences, to pay for even, printing of their PhD thesis or various kind of things. And we are also trying to encourage communication and dissemination amongst with social media, etc., by having webinars, seminars, etc., so that we can exchange views and ideas with different people on actually seeing how can we improve the situation. So I would be very happy to receive any kind of inputs from you all as to what do you think we can actually do to improve the situation. And I'll finally end with this, where we are actually looking forward to and hoping for a world where everybody has a freedom of choice. If somebody is interested in astronomy, he or she should be free to follow their interest, their passion. There should be equal opportunities for men and women to do astronomy without any reservation. There should be no reservation, neither in admissions, nor in awards, nor in anything. Women can compete on par with men. We just consider individuals as individuals which are non-gendered. It not just men, women, but all other genders should be, should not be given importance, because after all, other than our reproductive organs and hormones, we are all equal, right? So individuals should be considered individuals who can go ahead irrespective of their genders. And the best part about this is that this is all just to be doing astronomy, because astronomy is very beautiful, it's useful. First of all, because it raises us above ourselves. It is useful because it's grand. It shows us how small is man. I should change that to woman's body. How great his mind. You see, these are, I didn't change it in this because these are words of Henry Poincaré. And what you can see is how even in this, there's such a strong bias towards men, right? How small is man's body, how great is his mind, since his intelligence can embrace the whole of this dazzling immensity, where his body is only an obscure point, and enjoy its silent harmony. So, how I'd wish that Henry Poincaré had not written these words just for men, but inclusively for men and women. I kept it as it is just to show you that it is a battle we have to fight. It is still very much on. There is a problem, there is an issue, and we do need to work to, get this issue sorted. So thank you very much, and I'd be open for questions now.
Very much, Dr. Priya. It was a wonderful presentation. I really learned so much about all these people. One name that I generally recall is there was a female computer back in Johnson Space Center, Catherine.
Catherine Johnson.
Johnson, yes.
Yeah.
She played a remarkable role in Mercury 7, and it was because of her maths Alan Shepard was brought back to Earth safely, and everybody was stunned in the room based on her calculation, and he was supposed to trust her, and because of the same gender bias in their mindset, they were hesitant first, but the movie itself has been portrayed very beautifully.
Hidden Figures.
Hidden Figures.
See that. So actually, that's what. So what was considered at that point is that, it was considered all these calculations are very mundane and very boring, and therefore women were what were called human computers, right? And they thought that, this mundane job can be done by them because, but like I showed you how in the case of the Harvard computers, where even the so-called mundane stuff had lots of information sitting in it, and getting out that information is not trivial. The discoveries of Henrietta Leavitt, etc., it's not trivial. You have to put 2 and 2 together to then get something out of it. It's not just, mundane, monotonous stuff. There is, sorry, I didn't touch on that because actually, that astronomy and space research in principle are 2 different things, but generally, especially for school kids, younger people, they are much more attracted to the space research part of it. And that's why in the Indian scene, I added the ISRO thing because most youngsters are aware of, Chandrayaan, Mangalyaan, Gaganyaan,
Yes.
They know that more than the astronomers. So that's why I added that. But definitely in the space program, in India, all over, women have played definitely a very important role.
Right.
Actually, one should say, it would be fair to say an equal role. Because actually that's what we are looking for as a woman. I don't want a separate pedestal to be put on that. I'm saying let's be on par. There's no need of, putting women on a pedestal. That, like I said, there's no need to give reservations. Don't give
Yeah.
reservations. Let them compete, and we'll compete, and that would be a fair deal, right? People needn't think that so and so won a prize because he or she was a woman. It should just
Yeah.
be ungendered, and
Reservation is not really important, but I want to ask you this question based on the Indian mindset primarily. Like you mentioned, that the girl child is generally not very enthusiastically sent into science schools and things like that. In metropolitan cities, this is still very less, where the kids have the freedom to choose what they want to do. Mostly in tier two, tier three cities or in the villages. Like some of the names that you have mentioned, I was reading about them. They come from very small town where the facilities were not there. And at the time when there was no internet and there was hardly any facility available, where they have reached, it's absolutely stunning. Uh, what I want to understand is, for the audience also, there are a lot of female audience here with whatever little number we have. Uh, what is uh, uh, what is the government doing? Is there a special program to promote scientific temperament among girl child, or are there any specific courses to enlighten the people so that the females can be encouraged to pursue science? Is there something like that we can refer to?
yeah. So there are various programs which are being done by Department of Science and Technology. I mean, for encouraging women, there is a women scientist program. There's I think it's called Vidya Jyoti, and there are various programs which are being there, which are there. But the problem is obviously, you like you see in our country, the numbers are so large that see, another important thing also is that that we've been trying to work towards that children are given the idea that if you want to be a scientist, you've got to be super brilliant, and if you're super brilliant, only then you can do science, otherwise you cannot do it, right? And now the bulk of us, you, me, all of us, we are normal intelligence, average intelligence. Nobody is like some super, this thing. So everybody is average. But the problem is that people are given this impression that if you want to be this, oh, you've got to be like, the topper in your class, and you have to be something like that. It's not, people are given the feeling that they are not capable of doing it, right? This feeling of being not capable, right? In that, so what happens is, when the prizes or the amount of schemes which you have do not match with the number of students who want to do it, then the student says, oh, she was very smart, she got so and so fellowship because she was very clear, very smart, she cleared IIT JEE, IIT advanced, all those things, but I am not so smart, I did not do it, so hence I cannot do it. But I think we need to come to this point where the individual is respected, that if an individual likes a subject, right? For example, I can say I want to play an instrument, right? I needn't, I play the tabla, I needn't play it like Zakir Hussain. But if I like playing it, what's wrong if I play it? Right? So what we're talking about accessibility is that whoever wants to do science should be able to do science. They should not feel that you've got to be super intelligent to be doing that. Now, what happens with the schemes? There are many government schemes which are good and nice, but what happens is that since that goes to, you've cleared IIT, you've topped the board, you've done this, so that touches that crowd. But what about the others? Because like we have seen, specifically in the pandemic, I would say, the realization of scientific temper, of people being able to think scientifically, right, is so important. You would, I'm sure, agree to me with me that not only India, all over the world, the problem was handled most unscientifically, right? They did everything non-scientific. While we are now seeing that it is very essential that the scientific temper is there in the masses. And for that, science should be accessible to everybody. It doesn't have to be accessible only to the super brilliant. It should be accessible even to the average student who can do science, because that is important. We need it, right? Like I said, in the pandemic, see how people handle the situation. Basically, because the scientific temper is not there. People were willing to do anything which was unscientific, was most appealing to, I will not talk about because I don't want to discuss things like that, but anything which was most unscientific was most appealing to people. Moment you told them to do anything scientific, like go get yourself vaccinated, then people were like hesitant. That was not, likable. But the unscientific things, which I won't describe, people were very happy, very enthusiastic to do it. Now, where does that problem come for? It's basically because science is not trickling to the masses. If just one upper crust is just going to be doing science, the super brilliant of the country, then what about the others? The others also should be doing science because we need it. If we do not have that scientific temper in the rest of the people, then not only the pandemic but various situations, you handle it so badly, because. So I would say that what is important is that everybody does not have to be doing path-breaking science. Even if they can do regular science, at least they can train themselves to think scientifically, to question, to rationally, assess things. I think that's itself good enough. We don't need everybody to be, doing relativity or something like that. It's okay. But we have to be inclusive so that more people get into thinking, questioning, thinking rationally.
I have one small more question. You mentioned a lot about doing science or learning or understanding or doing science. What, according to you, is science?
So I would say the science is an organized way of questioning thing, right? To discover something. You want to scientifically answer a question. So how do you do it? You have a theory, you have a hypothesis, you experiment, you check on it, you deduce inductive, deductive, whichever way, and based on that, on solid evidence, on solid this thing, and then you do it, right? But which is rational thinking. There has to be rational thinking. So sorry, I kind of got it onto a wrong track, but I think that's the need of the hour, especially for our country and all countries. Even now, when we are hopefully coming out of the pandemic, rational thinking, I think, will really
I
help
think the
us.
pandemic has really taught us a lot of different things, and the most important being where our priority and focus should be. But nonetheless, this is a very important issue that the women contribution in science has usually been overlooked or not been appreciated much. And thank you very much for bringing up all these names, which are like hidden figures only. They did not get their due recognition. And I hope the students who have observed, who have watched the webinar today, will get an idea about how how they can really contribute in the field of science. I was very surprised. Most of the registrations, which are about 40-45 students who registered, most of them were female.
Oh,
So
yeah, I
yeah.
don't know why this is assumed that if it's women in astronomy, that women have to attend women in astronomy. Because I mean,
Nonetheless.
we had another meeting also today where we were discussing that this is not just a woman's problem. All men have women in their lives who are equally important and precious to them, right? So it is a common problem, right? I would
Uh,
not take it as a woman problem of women not being in astronomy. Men also need us, I'm sure.
So there are some thank you messages for wonderful presentation. They really enjoyed it. Excellent presentation, giving very useful information, ma'am. Thanks for this presentation. So I think the message is being received very well. And I'm sorry about the YouTube goof up. For some reason, there was some connectivity issue. Probably Google needed some permission. That's why that link didn't work. So we started doing another link. But nonetheless, the presentation, this whole session has been recorded, and by late evening, it will be uploaded. I'll send you the link as well, and to all the registered participants and other who could not register. I think because the schools have started, this is generally the time when the students come back.
Yeah.
Probably that's the reason they could not attend. So
I think, oh God, there's one question. What's the best way proceeding as an astronaut?
oh,
So, an astronaut is different from an astronomer. I will never be an astronaut. So, actually, if you see, Rakesh Sharma was basically from the armed forces, right? He's an Air Force pilot. So, essentially, for astronauts, what you need is very good physical condition. And in his case, I don't know how the selections have been made for Gaganyaan, but Rakesh Sharma was Air Force. I don't know for Gaganyaan on what basis did they do the selections. So it's basically a good amount of fitness, physical fitness is what is required. So, yeah, okay.
Probably if I can say something about it.
Yeah, please.
Uh, so Rakesh Sharma was primarily elected because of Indo-Russian joint effort, USSR at that time, towards collaboration in space. It was an intergovernmental contract, and they were looking for someone who was extremely risk taker, and Rakesh Sharma was a test pilot for Indian Air Force. His job primarily involved testing the aircrafts which have came out of service or there has been some technical glitch. So he would test those flights, and that was his the highlight of his CV. Kalpana Chawla became an astronaut based on her research in microgravity and its effect on human body. She flew into space twice. Unfortunately, the second was her last one. And Sunita Williams also, when she flew, she was also doing some research. Her research was also effect on effect of microgravity or zero gravity on human body in prolonged stay in space. So she stayed for I think about 340 days at a stretch. And apart from that, she had gone for a couple of more missions just to give her an acquaintance with the situation, how it would be in space. And Scott Kelly had a similar experiment going on. Most of the astronauts are selected based on the task at hand. So, for Hubble service and repair mission, there were more engineers than scientists who had gone. There was another teacher who went to space so that she can share her experience of going to space and being in space. Unfortunately, that also didn't end well in Challenger mission. But mostly the astronauts who are picked, they are based on the requirement of the mission and their expertise in that field. So, if you want to become an astronaut, you have to now become an expert in some field which our space research organization is going to work on in the future. Probably when we have our own Hubble Light Telescope that we launch, or if we have a joint venture with, another nation or another space agency, so probably you'll get a chance to work on it. But yes, you should be an expert in that field for which the missions are coming up, unless you want to pay money to Elon Musk or Jeff Bezos
Yeah.
and just fly out.
That would be the easiest way if you have the money.
Great. Thank you, ma'am. Thank you very much for your time. I'll share the link with you and all the participants in a bit as soon as the video is uploaded. And thank you very much, everybody, for participating. And I hope we'll have this kind of sessions coming in future as well. And I really appreciate your time for this. We discussed about 45 minutes. It's already been 90 minutes so far. So thank you very much for your generosity.
Yeah.
All right.
Thanks a lot.
Have a good day. And once again, happy International Women's Day.
Thank you. Same to everyone else. I mean, to all the women.
All right.
Bye.
Bye bye.